This research paper revisits the VerilogEval benchmark, enhancing its infrastructure and dataset to support specification-to-RTL tasks, in-context learning examples, and failure classification. The authors evaluate new commercial and open-source models, including GPT-4 Turbo, Llama 3.1, and RTL Coder, on an improved VerilogEval benchmark suite. The enhanced benchmark provides a more comprehensive evaluation framework for Verilog code generation tasks, offering insights into model performance and the efficacy of prompt tuning. The original VerilogEval benchmark only supported code completion tasks, lacked failure analysis, and was not conducive to exploring prompting techniques. The authors address these limitations by introducing specification-to-RTL task support, in-context learning examples, and a robust failure classification mechanism. The improved benchmark infrastructure uses a text file approach, allowing for easier scaling and human inspection of the dataset. The authors evaluate the latest state-of-the-art language models to determine the current frontier of LLM-based Verilog code generation. They find that recent open-source models, such as Llama 3.1, are becoming competitive with last year's closed models, and that prompt tuning varies considerably across models. The results show that GPT-4 Turbo achieves a 59% pass rate on specification-to-RTL tasks, while Llama 3.1405b achieves a pass rate of 58%, effectively matching GPT-4 Turbo's performance. The paper highlights the importance of understanding how different models respond to various prompts and contexts through the use of benchmarks providing granular failure feedback. The authors demonstrate that models can benefit substantially from in-context learning, and that prompt engineering is key to achieving good pass rates. The improved VerilogEval benchmark infrastructure is made publicly available, providing a valuable resource for continued model development and deployment in the field of LLM-based Verilog code generation. The research paper discusses the evaluation of large language models, LLMs, on code completion and specification-to-RTL translation tasks. The authors present a novel benchmark that classifies failures to observe the impact of prompt changes on code generation performance. They evaluate 8 LLMs, including OpenAI GPT-4 Turbo, Meta Llama 3.1405b, and Google Code Gemma 7b, among others. The results show that GPT-4 Turbo achieves the highest pass rate at approximately 48% for code completion tasks, surpassing the previously established state-of-the-art frontier. Adding an in-context learning (ICL) example further improves the performance to 58%. The paper also highlights the performance of open models, such as Llama 3.1405b, which matches the performance of closed models. The results indicate that larger models generally achieve higher pass rates, but resource costs and model-specific responses to ICL examples vary significantly. The authors conclude that GPT-4 Turbo and Llama 3.1405b are leaders in the benchmark, demonstrating the potential of open models in code generation tasks. The enhanced VerilogEval benchmark provides a more robust framework for evaluating the performance of large language models, LLMs, on digital hardware code generation tasks. This paper highlights that both Llama 3.1405b and GPT-4 Turbo push the frontier of performance with a 60% and 48% zero-shot pass rate on code completion tasks, respectively, surpassing the previously established 43% pass rate by GPT-4, non-turbo. Open-source general-purpose models, namely Llama 370b, and domain-specific models, RTL Coder, show favorable pass rates compared to last year's closed models, 37% and 32%, respectively. The addition of specification-to-RTL task support in the improved VerilogEval benchmark reveals even better model capabilities. GPT-4 Turbo achieves an impressive 59% pass rate in specification-to-RTL tasks, exceeding Llama 3.1405b at 56%, while Llama 370b and RTL Coder 6.7b also demonstrate strong competitiveness with pass rates of 42% and 37%, respectively. Adding in-context learning examples improves model generation accuracy in some conditions but degrades it in others, emphasizing the need for careful tuning of ICL examples to optimize results. The failure classification feature of the benchmark captures high-level counts of types of failures across different models and prompting settings, allowing for detailed inspection on a problem-by-problem basis within a run. This granular analysis helps identify whether specific problems or categories of problems have systematic types of failures. Such insights can guide more careful tuning of prompts across the benchmark, leading to more effective and targeted improvements in model performance. A careful analysis of the problem categories within VerilogEval and comparative failure counts could help find the best ICL examples to use for a given model. Here is a combined summary of pages 7 and 8 of the research paper. The authors highlight the importance of task-specific tuning to optimize performance in digital hardware code generation using large language models, LLMs. They demonstrate notable improvements in code completion tasks, with GPT-4 Turbo nearly achieving the same pass rate as Spec-to-RTL. The improved benchmark infrastructure, including the new failure classification feature, provides deeper insights into the types of errors encountered by different models. For instance, Llama 370B frequently encounters end module missing errors during code completion, which can be addressed through careful prompt tuning or model alignment. The authors emphasize the need for digital hardware benchmarks to be further expanded to include more tasks beyond RTL code generation, such as verification-related tasks, test bench stimulus generation, and others. The enhanced VerilogEval benchmark is designed to facilitate additional task support on top of a common set of design problems, allowing for a more comprehensive assessment of model performance for hardware design. The paper references various related works, including ChipChat, ChipGPT, RTLLM, and VerilogEval, which focus on the application of LLMs in digital hardware design. The authors acknowledge the contributions of NVIDIA Applied Deep Learning Research, ADLR, and the NVIDIA Inference Microservices, NIM, teams to this work. The authors also discuss the importance of understanding and mitigating poor code generation, which can be achieved through the ability to classify and inspect failures on a problem-by-problem basis. This can lead to more effective and targeted improvements in LLM performance for digital hardware code generation. In the future, the research community would benefit from further expansion of digital hardware benchmarks to include more tasks and design problems, enabling a more comprehensive assessment of model performance for hardware design.